Hi, this is Debjit from University of Illinois at Urbana-Champaign. I'm going to present my work, GOLDMINE, a tool for enhancing verification productivity. With ever-increasing design complexity, hardware verification has become one of the most critical tasks of modern hardware design cycle. The cost of an undetected bug is extremely high in terms of performance and loss of property or life. Hardware verification validation includes both pre-silicon verification and post-silicon validation to ensure that the design is correctly implemented as per the specification. In industry, hardware validation is a primary bottleneck of the entire hardware design cycle. It incurs more than 70% of overall time and resources and takes up to 2 years. This is primarily due to the sheer size of a modern hardware consisting of billions of transistors, hundreds of different functional blocks, and tens of different functionality. Going forward, as we design more and more complex hardware systems, the validation problem will become increasingly more difficult. Hence, hardware validation is an extremely important and difficult problem for current and next generation hardwares that needs to be addressed immediately. Hardware verification includes a plethora of tasks such as design understanding, design summarization, debugging, and bug localization. For each such verification task, various methods were proposed by the researchers in the past decade. All those methods can primarily be categorized as static analysis-based techniques or dynamic analysis-based techniques. Unfortunately, the verification is always a battle of scale, and almost all verification methods suffer from the scalability issue. Static analysis-based methods analyze design source codes without actually executing the design. Static analysis can make excellent generalization, but is computationally intensive. On the other hand, data-driven dynamic analysis-based techniques, such as machine learning methods, are computationally efficient, but lacks domain knowledge and perspective. In GOLDMINE, we inherit best of both worlds. We perform lightweight static analysis of design source code to gather necessary design domain knowledge such that the machine learning techniques can be guided with adequate perspective to perform a plethora of verification tasks. GOLDMINE was originally developed in 2010 as an assertion generation tool. In recent years, we have modularized key components and repurposed GOLDMINE by integrating a plethora of new features. These have enabled new use cases of GOLDMINE across a wide spectrum of verification tasks, thereby enhancing GOLDMINE's viability beyond its primary goal of assertion generation. GOLDMINE consists of 5 principal components: static analyzer, dynamic analyzer, assertion miner, formal verifier, and assertion analyzer. In the next few slides, we are going to discuss the intuition of each of the components and their workings. In the first use case of GOLDMINE, we discuss design understanding. To understand the design, we use static analyzer. Static analyzer is an ensemble of multiple complex algorithms that can extract multiple design information and store them in appropriate data structures. This data structure can be used independently for various verification applications such as design understanding, design interpretation, and identifying opportunities for design optimization, and also to remove design redundancies. To explain the different data structures that GOLDMINE creates, we will use the 2-port arbiter as our running example. To capture both the control and data dependency among design variables, GOLDMINE constructs a variable dependency graph, or VDG, where each node is a design variable and each edge between a pair of nodes is either a control or data dependency. For example, in this 2-port arbiter, there are 7 different design variables, and hence the VDG has 7 different nodes. Each directed edge either represents a data dependency and control dependency. For example, GNT underscore and GNT2 has a directed edge, which represents that GNT2 is control dependent on GNT underscore. GOLDMINE can also identify other important design structures, such as important design variables with respect to a given design output, the dependent symbolic functional dependencies of a variable in the context of a particular design output, and the sequential dependencies of a design output over other design variables across multiple clock design cycles. In this example, we consider the primary output variable grant1, and in order to understand the sequential dependencies of grant1, on other design variables over multiple clock cycle, we unroll the design for 2 clock cycles. Essentially, in this graph, we see that grant1 in the first cycle is dependent on grant underscore, and by transitivity, we see that GNT1 is also dependent on the value of grant1 in the previous clock cycle, and so on and so forth. In addition to variable dependency graph and to find out the sequential dependencies, GOLDMINE can also construct control data flow graph or CDFG for a complete design to capture different control paths and data flow across each such paths. We use all these different static analysis information in multiple downstream components of GOLDMINE. The next use case for GOLDMINE is design behavior summarization. Summarizing design behavior refers to generating assertions from simulation traces. Assertion generated from simulation traces can generate succinct explanation of the simulation data. It consists of 2 parts. The first part is generating simulation trace data as a behavioral signature of a design execution, followed by design behavior summarization by systematically mining assertions from trace data. The generated assertions can be used as golden design specifications in a system level reference model or as guidelines for future design enhancements and optimizations. To generate the simulate trace data, we simulate the design with a random test bench. Alternatively, a user can provide a custom trace data file by simulating the design with a user-defined constraint test bench. In this example, we use the code snippet and the random test bench to generate simulation trace data as shown in the table. We use this simulation trace data as input to the assertion generation phase. In the assertion generation phase, given the static analysis information gathered by the static analyzer and the dynamic trace information as generated by the dynamic analyzer, our objective is to generate high quality assertion to summarize design behavior. In GOLDMINE, we generate assertions of the format G always A implies C, where A is the antecedent, C is the consequent, and A, the antecedent, essentially consists of M different propositions, and we usually generate assertion in the sequential format. In GOLDMINE, we have integrated multiple different assertion mining engines. Of them, three are available immediately, namely Decision Tree Miner, Bayesian Decision Forest, and Prism. The other 2, Coverage Guided Miner and Counterexample Guided Miner, are in development and will be available by the end of November. In the next 2 slides, I'm going to explain the working of 2 miners, namely Decision Tree Miner and Coverage Guided Miner. To explain the decision tree miner, I use the design source code as shown in the left. Clearly, from the code, it's apparent that if there is a valid integer writeback indicated by the variable int.valid and the register is available indicated by the variable int.hasDrange, then there is a valid writeback on port 0 as indicated by the variable wbvalid0. We use decision trace miner to generate this assertion from the trace data of the trace data in the table. The decision tree-based miner recursively partition the data space by assigning values to feature variables until the value of the target variable is consistent within a data subspace. In this example, wbvalid0 is the target variable, and the remaining variables, namely int.valid, int.l1hit, and int.hasDrange, are feature variables. The mu of a node is the mean value of the target variable within the data subspace represented by that node, and the error e of a node is the mean absolute deviation of the value of the target variable from the mean of that node. The objective of decision tree mining is to reduce the error of a data partition to 0 such that target variable becomes consistent with the data subspace. As shown in this example, if we do not include the static analysis information during the mining process, then we can generate assertion where we can include propositions that are not causally related with the target variable. For example, in this case, int L1 hit is definitely, it's not causally related with the target variable of wbvalid0. And that's why it generates a wrong assertion as shown in the right-hand side in red. This motivates us to guide the data miner with static analysis information. After we replace int.l1 hit with int.hasDrange, which has a causal relation with wv valid 0, we can mine the intended assertion, and as shown in the green color on the right-hand side. The decision tree miner has several shortcomings. We explain with an example. For the target function of z, we construct a decision tree which generates two correct assertions, A2 and A3. But the inspection of A2 shows that the proposition A is coincidental. The presence of such coincidental propositions make an assertion overconstrained, unreadable, and achieves low input space coverage. To address this problem, we introduce coverage-based miner. In the coverage-based miner, we introduce a four-step process where we first generate candidate assertions, then we identify the amount of simulation traces that are covered by each of these assertions. If an assertion covers a minimum amount of input coverage space, then we retain that assertion. Otherwise, we discard that, and we reduce the gain or the minimum input space coverage that is needed by an assertion for the next assertion, for the next iteration. And this process continues until the entire input space coverage as given by the dynamic trace tracer is covered, or we reach a minimum value of input space coverage. The next use case of GOLDMINE is assertion rank analysis. To enhance verification quality, it is imperative to use high quality assertions that can capture subtle and important design behaviors. To automatically identify such high quality assertion, constructing a quantitative figure of merit is a critically important problem. We have implemented such a ranking scheme to identify the set of most valuable assertions for verification tasks in the assertion analyzer. Given that GOLDMINE assertions are targeted for design verification, design understanding, debugging, we investigate how we can quantify good assertion. Intuitively, we believe that an assertion should be ranked based on its characterization of design functionality. To rank an assertion, we identify two component metrics: assertion importance and assertion complexity. We explain each of these metrics with a simple example. One can see intuitively from the design graph that there are multiple design behaviors, which of them represented by a path from the origin node to the destination node. Also, any behavior in a design can be considered important if that behavior affects the visible output of the design. The more subtly it affects the output behavior, the more important it is. One way to quantify and compute this functional notion of importance in terms of design structure is to find variables that are highly connected to other important variables. An important assertion for a target variable would then be one that comprises many important design variables and captures design paths that are most important to that target or output. In this example, both P6 and P3 affects GNT2 starting from the origin blue node, but P6 affects more slowly, more subtly. Hence, P6 is more important assertion than the P3. However, too many important design variables in an assertion hinders its understandability and diminish its practical usability. The anticipated use cases, such as design understanding, validation, and debugging of our ranking method, tend to have a human in the loop who needs to comprehend the design behavior as captured by an assertion. In order to balance the importance with understandability, we calculate the complexity of an assertion. The resulting assertion complexity is an attempt to quantify and compute the human comprehensibility of an assertion. Intuitively, we consider the complexity of an assertion to be the number of logic level traversed from the assignment of a variable and the consequent of an assertion to the reference of the variable in its antecedent. Our reasoning is that understandability decreases with traversal of more logic level when the source code is being inspected by a debugging engineer. Hence, our approach ranks important assertions that are understandable highly. We compute ranks for propositional as well as temporal assertions. In this slide, we show some examples of the assertions that we mine for this two-port arbiter. The assertion B0 represents a subtle and temporal behavior that is not directly observable from the source code, and hence it is ranked higher. But the assertion B3, it is a verbatim translation of the source code and is immediately visible from the source code, and hence it has been ranked lower. The other component of assertion ranking analyzer is a SRank analyzer. In this, we use a correctness-based statement coverage algorithm for an assertion. Intuitively, we try to identify the design statements that must execute for an assertion to be true. For that, we use an antecedent constraint simulation of the design. We constrain the design signal values equal to the value as mentioned in the antecedent. Any variable that is not assigned by the antecedent is randomized. Then we execute the design until the consequent is evaluated and record the set of statements that are executed and dependent on antecedent. We repeat this process for a user-specified number of times to simulate more design paths. The final set of covered statements reported are the set union of the statements covered in each iteration. To explain this idea, we consider this example. The assertion essentially assigns the value of the first bit of I2, the 0th bit of I2, and the reset signal. Once those values are assigned, we randomize the other signal values. And once we execute, then we find the S2 is executed. Also, S7 is executed because of the reset signal. Once case I2 is executed, since I2 is assigned a value of 0, S3 is executed. And also, since reset is true, S8 is also executed. And since we see that R1 is executed and in statement S8, and S1 is a continuous assign statement, so S1 is also executed in the second step. In total, for this assertion P to be true, statement S1, S2, S3, S7, and S8 needs to be covered. We rank an assertion higher if it covers more statements. That means that particular assertions cover a larger design space, a larger design behavior space. The final use case of GOLDMINE is debugging and bug localization, where we repurpose the different components of GOLDMINE. During the debugging and bug localization, lots of dynamic traces are produced that are failure signatures of a design. We consider each such failure traces, analyze the design with static analyzer, and summarize the failure traces in terms of assertion, which we call symptoms. Once we have failure symptoms for multiple failure traces, we find out the common symptoms that across multiple failure traces. Once these common failure symptoms are available, we use SRank analyzer. And we use SRank analyzer to find out the statements that are covered by those symptoms. And we propose that the statements that are covered by those symptoms are most likely the buggy codes that needs to be further investigated. Finally, addressing a few reviewer suggestions, our tool intimately depends on a formal verification engines that's available commercially. So the reviewer suggested to make it dependent on open source tool. But since GOLDMINE generates assertions in sequential format, we couldn't use the open source EOSys open synthesis suite. But recently we have acquired the academic license from Symbiotic EDA, and we are working on integrating the Symbiotic EDA EOSys formal engine with GOLDMINE so that the dependent on Cadence IFV can be removed. We expect that this will be available by November 2020. Finally, to summarize, GOLDMINE adds lots of values to the EDA community. It is the first open source scalable modular toolset for hardware analysis and verification. It represents a systematic, it creates a systematic representation of highly valuable multiple design perspectives. We offer repurposable data structures containing important design information, and we also provide APIs for additional hardware analysis task integration. The GOLDMINE is available from these above websites. The users can also fork the repository, can report any issue they may find. If you are interested, please fork this repository, create pull request, and if you want to collaborate, please contact with me or with the Professor Vasudevan. And thank you.